Welcome. This question says a 3 kilogram block is stationary, but on the point of slipping. What is the coefficient of static friction for the block and the incline? And this diagram over here tells me that the mass of the block is 3 kilograms and the angle of inclination between the slope and the horizontal is 20 degrees. I don't like using the diagrams provided, so I'm going to draw what I think is a better diagram. I try to make the angles quite reasonable. I try to avoid them looking like 45 degrees. Many times people draw all their angles at 45 degrees. And of course this is Fn. There's always a normal force when a block's sitting on a surface. And there's Fg, and that equals mg, and that equals, in this case, it's going to be 30 because it's 3 kilograms. And then for along the slope, of course, we have a frictional force, Ff. There's no mention of an applied force, and there's no reason to believe there is an applied force. It's just sitting there, and so there would not be the need for a force up the slope or down the slope or whatever. Looks to me like we have three forces, and they're in equilibrium. Let's try to get to the answer. The question says, what is the coefficient of friction? So Ff for a static system is less than or equal to mu s times Fn. But because we're on the point of slipping, it means that we have the biggest frictional force we can deal with. And so in this case, we can say it's equal to. So that means that coefficient of static friction in this case is equal to Ff over Fn. And we were here just in the previous problem, actually. We were here, except in the previous problem we were on the horizontal. So let's use the same systematic approach. We're going to say find Ff using, and I want to pick an axis which will give me Ff or a component of Ff so I can get an answer. More to the point, I want to pick an axis in which I don't have to deal with any other unknowns, and I don't know what Fn is yet. So if I'm a little bit proactive and I choose to pick the axis along the slope, then Fn is not included. Ff is included, and of course there is a component of the weight, and I hope you get into the stage where you can simply say that this would be 30 sine 20 newtons. So along this slope I have Ff, which is in the line of the slope, and I have a component of the weight which is 30 sine 20. Let's make this end positive and this end negative. So I'm going to say plus Ff. Oh, I'm sorry. I didn't actually formally tell you what I was going to do. Because it's in equilibrium, I can say the sum of the forces along the slope equals 0. I'm relying on the fact that we have equilibrium along the slope. So now I can go to the more detailed answer. So Ff plus, well, that's pointing in a negative direction, so it's going to be minus 30 sine 20 equals 0. So Ff is equal to 30 sine 20. I'm going to leave it like that because I know a little trick, which I'm just going to show you. You can numerically evaluate it. I'm not doing anything that is special. You can numerically evaluate it, or you can just leave it and do all the numbers at the end. I'm going to leave it and do the numbers at the end because I want to show you something. And so we have this guy here, and we can say, okay, let's find Fn using, and again, although I have a value for FF, I'd like to use this same methodology where I try to avoid it. Let's just try and find Fn using by itself using a good axis. And so I'm going to turn around and say, okay, do this in red. I'm going to pick that axis there, perpendicular to the slope. That means I have a downwards component, and this would be 30 cosine 20 from my trig, and then Fn, of course, is along this line. The key point is FF is not. So then I say, let's call this positive, let's call this negative, the usual stuff. So I say plus Fn added to minus 30 cosine 20 is equal to 0. Again, let's just leave it in that form. So now I can say, well, mu s is equal to FF over Fn, which equals, well, 30 sine 20 over, oh, look at that. Let's just finish this bit off. FF equals 30 cosine 20. So this is over 30 cosine 20. Well, the 30s cancel, and actually a sine over a cosine is a tangent. You know, opposite over hypotenuse divided by adjacent over hypotenuse is opposite over adjacent, which is tangent. Tangent 20. And it's just a clever little, well, not clever, but it's just a unexpected little surprise. So mu s is equal to the tangent of 20. So tan 20 degrees is equal to 0.36. And again, we've said before, newtons over newtons means no units, 0.36. And my answer is B in this case. Now, let me just talk about this answer a little bit. What this means is that if I do want to find the coefficient of static friction of a block on a ramp, all I need to do actually is tilt the ramp to higher and higher values. And when the block starts slipping, I look at this angle and I find the tangent of it, and that is the value of the coefficient of static friction. It's a nice little unexpected result. Doesn't matter what the mass of the block is. If you just tilt the block on the surface that it sits on, at the angle at which it begins sliding, that will tell you, the tangent of the angle will tell you what the coefficient of static friction is. So what did we do? We basically had a good diagram. We figured out that we wanted FF over Fn. We said about finding FF by excluding Fn from our resolution of forces. We realized we'd have to resolve our forces along the slope. We then tried to find Fn without involving Ff, so we realized we could resolve our forces perpendicular to the slope. Again, I didn't write that down, I'm sorry. The sum of the forces perpendicular, put a little perpendicular slope, equals 0. So I resolved my forces along the slope to find Ff. I resolved my forces perpendicular to the slope to find Fn. And then basically I substituted them in. And what the unexpected result that came out was that mu s is numerically equal to the tangent of the angle at which the block starts slipping. And that was not expected. So there we have it.